Good morning. Let us start. So, as I wrote you yesterday, we will do a small change in our course. And the reason is very simple. We have lost several lectures. So we are lagging behind by something like 3 lectures compared to what has been usually. So not so easy because we still need to finish by the end of March. I will see how we will do. There may be need for some more changes or simplifications. So it can happen that I will either omit some parts or maybe do it in shorter way. And that, of course, I will also take them into account with exam. But now we skip at the moment uncertainty calculation for linear regression. And the plan is as follows. I'm going to show you. So there is the example, there is the calculation example file on Moodle, which you will easily find, this one. And instead of doing this in class, please, each of you, try to do yourself. You are more than welcome to discuss among yourself, etc. I saw that some of you actually have already solved the respective homework completely in Moodle. So try to do yourself, and if you do not manage, then I will find a way to help you. Yeah. And let me just give a very, very brief explanation here. So essentially, this is here your model. Slope B1, intercept B0. You will calculate with slope and intercept functions. You find easily in help how to do. And basically, you calculate here the concentration of the sample from all these data, whereby these 3 concentrations, 3 absorbances or 3 signals, you put into the slope and intercept functions. And then you do the typical Crachten calculation as we've done already here. So there's nothing special here. And also these components and indices, you know all that. Yeah. So please try. And maybe somewhere, let's say like next week or so, I will bring this up again. And let's then see how you have managed. Yeah. Any questions at this point? I think having heard what you have heard here already about these things, you should be perfectly able to do that actually on your own. And indeed, please do that at home so that when I ask next time, I would not like to see that, no, I did not do, no, I did not try, etc. Yeah, so if you don't manage, okay, but please try. And if you see that it works, then go immediately and try the homework. And again, this example, you are more than welcome to join forces, discuss among yourselves. So, any questions here? If not, then any questions about anything else related to this course before we start? Okay, if not, then we will move on. And now we are leaving, finally, the biggest part of this course, which is this measurement uncertainty, but it, of course, as you noticed, gave a lot of additional fundamentals and background things. And now we are moving more towards different, if I may say, tools and applications. And the first very important tool are reference materials. So this is what we will start today. Very important for method validation, uncertainty estimation, recovery determination, achieving traceability. So we just cannot be overstated how important reference materials are. And first, about classification, terminology, definitions. So reference material is a material which is sufficiently homogeneous and stable, with reference to specified properties. These properties, in the case of chemistry, most of the time are analyte concentrations. So it can be something like milk powder, where the amounts of trace elements are known, or drinking water with heavy metal concentrations determined, or some meat with veterinary drug residues determined carefully, etc. Which has been established to be fit for its intended use in measurement or in examination of nominal properties. So we here only are, let's say, concerned with measurements. Nominal properties are all kinds of, let's say, non-measurement like things, such as, in principle, it can be something like taste, odor, color, and all those things, which we do not do. So as you see, this is a very relaxed definition. Essentially, anything that is stable and homogeneous, and where something, concentration of something has been determined, is a reference material. So as we will see in the coming slides, any calibration solution that you make in the lab here, in the lab, is also by definition a reference material. Okay. Here are some examples. So it can be indeed something like water with known content of trace elements, milk powder with protein. It can be pure substances, pure elements, and it also can be standard solutions. And then all kinds of technological, etc., things also. So very, very wide definition. And as I already said, in principle, any calibration solution that you make in your lab is a reference material. And oftentimes there's a special term for those reference materials that you make in your lab. And these are often called lab reference materials or laboratory reference materials, LRM. But now, which is actually somewhat more interesting for us, are certified reference materials. So most of this part of the course is actually concerned with certified reference materials, not reference materials more widely. So certified reference materials, they are a subgroup of reference materials. So certified reference material is a reference material accompanied by documentation. And by document, usually we mean certificate, by an authoritative body. Authoritative body typically is some reference material producer. And reference material producers typically are very high level, highly competent labs or organizations. And they provide one or more specified property values, again, property values, which again are concentrations of analytes in most of the time, in chemistry. And very importantly, here it's not simply property values, but they have uncertainties. So those people who have determined those property values have also established what are the uncertainties of those values and traceabilities. So the values are traceable nowadays typically to the SI, the SI system of units. Traceability will come at a later stage of this course, and then I will tie together certified reference materials and traceabilities. Right now, we simply can memorize that traceability is something very important in relation to certified reference materials. So certified reference material is something that you buy together with some certificate which says how much is inside of something. So that, again, you can buy milk powder, with, for example, some polychlorobiphenyls determined in that milk powder at high level and with measurement uncertainty. Or you can buy certified drinking water where all the elements are listed, all the concentrations and all the uncertainties also. So this was classification by status, what they are. Now the next thing is by composition. To some extent I already mentioned. But now we can look more. So first of all, they can be pure substances. So you can buy pure metals, pure oxides, salts, etc. Some of them are simply reference materials, but pure substances can also be certified reference materials if they have determined purity carefully and give uncertainty for that purity. Most pure substances that you can buy from producers are not certified, but some of them are. Then you can buy solutions. This is quite common, for example, in ICP-MS analysis. Those of you who took atomic spectroscopy, you may remember I explained that also there. Many people nowadays who do ICP-MS analysis, and if they need to determine many elements, they don't start, okay, oxide of this element, now I dissolve, okay, now I make such, okay, now I take the next element, it's a lot of work. Instead, they buy a solution where there might be 40, maybe 50 different elements inside, all known with concentrations and uncertainties. Those solutions are usually like concentrated, quite concentrated. But people can then do dilutions in their own laboratory and make calibration graph with those solutions. And if they are certified reference materials, they also immediately provide traceability for that measurement, which is very important. So it can be one analyte, can be several analytes, can be analyte and some interfering compounds. So that solution may have put in on purpose some compounds that are likely to interfere with the measurement. Then it also enables mimicking real-life situation, enables validation, etc. Then it can be different kinds of artificial mixtures. What I mean by artificial mixtures is, for example, some solvent mixtures. So some kind of solvent used, for example, for diluting paints or some industrial things can contain several compounds, and you can buy such mixture and telling you, okay, there's acetone this much, ethyl acetate this much, butyl acetate this much, and maybe toluene this much, is inside. So this kind of mixture. It also can be some kind of plastics or industrial concentrates, and also alloys, metal alloys. Metal alloys are also artificial mixtures because humans have made them and put in different metals. And you can buy metal alloys with carefully determined how much of every element is inside. Finally, what is perhaps the most interesting for us are matrix reference materials, and especially matrix certified reference materials, which sometimes are called certified matrix reference material or matrix certified reference material. And these are of particular interest to us because these are now the ones that I mentioned. You can buy soil where phosphorus, iron, etc. elements are determined. You can buy blood plasma. You can buy drinking water. You can buy some meat powder which has been dried carefully. You can buy rice, flour, you can buy wood chips, for example, where some constituent has been carefully determined, etc. So these are reference materials that mimic real-life objects. This is their aim, that you can buy samples that are like your samples that you do analysis with, but you know how much is inside, how much of the analyte is inside. And actually, when I mentioned here alloys with artificial mixtures, in principle, alloys can also be here in this pot, because alloys can also be your real samples in your real analysis. It can also be wine, it can be olive oil, it can be essentially anything. And they can also be different types, different subtypes. We will come later to production, how certified reference materials are produced. I will explain you, actually not so much later, quite soon. But let me already say here that these matrix reference materials, which mimic real objects, they first of all can be natural. Now, natural means that, okay, I want to make a tree leaf, for example, oak leaves, reference materials of oak leaves. Yeah? Oak is a tree. Yeah? So what do? Yeah, I find somewhere in the forest oaks, and now I collect those leaves, a lot of them. I bring them to the facility, and then they homogenized and mixed and so on, and bottled, and then determine some constituents. This is what natural means. You simply take what is there. Okay. But suppose you want some trace element, trace toxicant, etc., certified reference material, then those oak leaves might be very clean. Yeah? There's not much inside. And occasionally you may want to have higher levels of that contaminant or toxicant. So then you can do incurred reference material, which means that, okay, suppose it's some kind of plant. The plant grows here, and now you feed that plant. You put water. You put water to the plant, but the water is not just water. It has high level of lead in it, for example, or cadmium, or both lead and cadmium. So you feed to the plant water which contains high levels of the toxicant or the contaminant. And now the plant takes the water, lead is diffused into the leaves, and then the cadmium, etc. And when you now collect those leaves, they have high levels of those toxicants. Now you take it to the lab facility and you make the CRM, and now you have higher concentrations. This is what fortification means. And this fortification is done, although I'm not calling it natural, but it's still natural in the sense that lead ends up inside plant via roots and so on. As the plant grows, the lead like diffuses into the plant. But of course, this fortification not so easy to do. Yeah, you have to have somewhere where that plant grows. You have to have a garden or some growing facility. Somebody has to take care of that plant, go with the water, put water all the time. So it's costly. And also, suppose you want to do some fortified reference material, for example, for veterinary drugs. You want to have high level. You want to have high level of veterinary drug in beef, for example. What you need to do for that is you have to have a cow whom you have to feed those veterinary drugs at high levels. Yeah, well, having a cow is not the simple thing to do. You cannot just have it. You have to have a facility, or you have to contract. Usually those places which make CRMs, they don't own farms or gardens. They contract with somebody. So for example, there's some facility where there are maybe hundreds or even thousands of cows, and they make a contract. Okay, this particular cow is fed more veterinary drugs than the other cows. Yeah. And finally, then this CRM facility buys this cow when the cow is slaughtered eventually. Yeah? Then that meat, of course, cannot be sold because there's very high level of veterinary trust. That what do I say now? Body of the cow is then transported to the facility. The meat is taken and processed and so on. Now you get a meat which is rich in veterinary drugs. Of course, you can imagine this is pretty costly thing to do and pretty complex, and you need to find somebody who agrees to do all that and so on. So it's not really easy. Yeah? So that there's alternative thing which is simpler, which is spiking. Spiking means that, okay, the cow grows as it grows, yeah, or plant or whatever. And now you can, or the facility that produces CRMs can buy cow meat essentially in any shop, yeah, or anywhere, bring the meat to the lab, and now during processing, add additional veterinary drugs there. So it's minced, it's mixed well, and now you put more veterinary drug in. The same can be done with plant leaves, etc. But now question to you, which one of these two options gives you better imitation or better mimicking of the real life situation? Okay, everybody says either incurred or fortified, and this is correct answer, yes. Because, for example, if you take those plant leaves and now you try to mix lead into it, the lead will not go inside cells the same way as it would if the plant gets water from the soil and then the salts will diffuse throughout the plant. So spiking with some matrices is okay, but with some matrices it does not work so well. In any case, as you see, you perhaps already imagine it's not very easy to make certified reference materials. And we will see later on that this indeed is a big thing. Yeah? Production of certified reference materials is not an easy task. So let me stop for a moment. Any questions here? Anything anybody wants to ask? Anything anybody wants to ask? Okay, if not, or perhaps let me ask then, please raise your hand who understands this logic here. So one person did not raise hand, okay. But in any case, yeah, it will still be possible to ask questions at any moment. So now the next thing is classification by the meaning of the reference value. And this is now a tricky one. Yeah? This is more difficult to understand than the previous ones. There are mainly two possibilities. The reference value can be independent of the method, or it can be method dependent. In this case, it's just, let's say, the content of lead in some kind of matrix. In this case, it's something like, let's say, extractable lead, bioavailable, etc., etc., etc. And this is a very important thing, because if we speak, for example, some nutritional elements, let's say phosphorus in soil, then the total phosphorus and bioavailable phosphorus in the same soil, the amount can differ by several times. These are completely different things. And when I say here method dependent, occasionally in the slides, I have the word procedure. And here procedure and method is the same thing. So whenever you see procedure dependent or in any way procedure, you just consider that this is the same thing as method. So what is, how is it this method independent thing? This is total, for example, if it's total content of boron in the soil, yeah, then this means that the total mass of boron atoms relative to the sample mass, yeah. For example, how many micrograms per kilogram of boron is in soil, or how many micrograms per kilogram of lead is in that river sediment. And here, it's not really important which analytical technique you use. All techniques that give you the total amount are fine. For example, digestion can be done in different ways, yeah, etc. The only important thing is it has to give you the digestion or sample preparation, and later the analytical method itself has to give you the total content. And if one did it with one method, the other one did it with the other method, you still can compare the results. But if we speak about method-dependent values, then these are always linked to a method or linked to a procedure. For example, bioavailable boron in soil. When I say that in the case of bioavailable phosphorus, the difference might be several times, then I've heard from soil chemists that bioavailable boron is typically 10 times lower than total boron. So that most of the boron in the soil is not bioavailable. Only 1/10 or so. So you see, they're completely different things. Yeah? And here, we essentially need to determine only the part of boron that really is available to plants. And how do you know, or how do you determine what is and what is not available to plants? There is always specified some extraction method. For example, in all those bioavailable elements in soil, which is actually a pretty important part of this method-dependent reference measure. Bioavailable elements in soil, it means that you take the soil, you suspend it in some kind of liquid, which typically is some kind of buffer solution, aqueous solution with some fixed pH. Then you put it at a certain temperature, and then you stir for a certain time, and all this has to be explicitly given in the method, and you have to do as method specified. And once that stirring is finished, you filter, you get the liquid, and now you analyze the liquid. And the liquid tries, or this whole procedure tries to mimic the way how plants get the same element from the soil. Yeah? So that only part of the element is extracted into the liquid. Obviously, I think we all agree that if one does this stirring at one temperature, the other one does at higher temperature, then at higher temperature probably more is extracted. Yeah? Or if the pH is different, or the amount of liquid is different, or one is stirring during longer time than the other. So all these technical details need to be fixed. And if different people used different extraction procedures, they get values that are different and cannot be compared. You know? So, as I said, important to closely follow the method, and results cannot be compared if several labs used different extraction methods. Let's see now, how is it now? Please raise your hand who thinks that understood this logic. Okay, good. People on the internet. Everybody understood. Very good. Now let me ask this question from you. Okay, you see, this is very inconvenient. Yeah, you have to use the same method, etc. It's much easier for everybody to use method-independent values. Why do they make such certified reference materials which have method-dependent values? Why are they needed? Why? Why do we take this hassle? Could you take the microphone?
Maybe because method-dependent reference material had the same metric as the real sample.
Yeah, but the same matrix as the real sample can also be with the total values, no?
With the correction value of extraction?
I did not understand. Maybe you thought, maybe you are giving the right answer, but I don't follow the logic now.
I mean, because if we use like control reference material, is just the value that we add, but for this method, we correct some loss of extraction
No,
or
it's
sample
not.
preparation?
No, it's not loss correction. No. Could anybody send anything to favor? Yeah.
I think phosphorus, we are more concerned about bioavailability than total concentration or total content.
Exactly. If you are a farmer, you don't care how much boron overall is in soil. You only are interested how much your plants can get it. The same about phosphorus and the same about essentially anything. So in soil analysis, it's very important to make distinction. I'm not so good in boron. I don't know so well the chemistry, but with phosphorus, it's very clear. You probably know that phosphorus can be in different phosphates, hydrogen phosphates, and dihydrogen phosphates. And a large part of phosphorus, at least in this country in soil, is calcium phosphate, calcium 3PO4 2 times. Yeah, that is a totally insoluble compound. Plants cannot get anything from it. So the plants only can get phosphorus from hydrogen and dihydrogen phosphates if they are in soil. So that is the part of soluble phosphorus. Yeah. And there's probably something similar with boron also. So that the need for method-dependent or for CRMs with method-dependent reference values comes from practical applications. People who ask analytical chemists to do analysis need those values. They don't need total values. So for farmer, total phosphorus is not really as important as bioavailable phosphorus. And here is an example of a certificate, shorthand, of course, not the whole certificate is presented here. So metals in river clay sediment, yeah, river clay sediment. And you notice there are total metals and extractable metals. You know? And the extractable metal content refers to metals soluble in hot aqua regia. Who knows what is aqua regia? Who feels uncomfortable when I say aqua regia? Some people, yeah. Aqua regia is the mixture of hydrochloric and nitric acid, 3 parts of concentrated HCl plus 1 part of concentrated HNO3. So this is what is aqua regia. Yeah. Okay, so there's some aqua regia extraction, and it's not just that, okay, I take aqua regia, I put the clay sediment in. There's a whole standard about it, which explains exactly how much you take, what is the temperature. Yeah, it says here hot, but it's not just hot. It's some predefined temperature, of course. How long do you extract, and so on and so forth. Yeah. So, according to this standard. Total metal contents, then you can determine using different techniques, and in fact also the extractable metals afterwards you can determine with different techniques, but extraction has to follow this ISO standard. And now if you look, many of the metals are present in only one of the lists, and some of them are not very different. They're like copper is here 96 and 92, not so different. Yeah. But some metals are very different, like chromium is perhaps the most different. Here it depends on which way you look at it, but it's more than 1.5 times higher, the total amount compared to the extractable amount. So this is very, very important to clearly specify which you are determining. And of course, I think you all understand that whenever you do the analysis, then your measurand definition or the definition of what you are determining needs to be very clearly written. Are you determining total elements or extractable elements? Yeah? Or total phosphorus, bioavailable phosphorus. So, anything you would like to ask?
So physically they are the same.
Sorry?
So physically they can be the same object with like metals and extracted metals?
They are the same, yes. It's the same bottle. Yeah, it's good that you ask. I did not think that I have to. It's the same bottle, there's the clay inside. And all these values count for the same bottle, depending on which way you do sample preparation. If you digest in such a way that everything is decomposed, you get the total amount. But if you extract with this ISO 11466 method, then you get the extractable amount. So it's the same clay, yeah, the same amount of metal inside. It only depends on how you do the sample preparation. Now we move to production of certified reference materials. First of all, we look at the matrix certified reference materials, and maybe not so high probability that you will be producing certified reference materials in your life. So we will not go to very great detail, but I think it's very useful for you to know in general what it consists of. Also, who knows, yeah, you may end up somewhere where you need to produce certified reference materials. So what you need to do is, first of all, you need to prepare the material. You need to determine that it's really homogeneous and stable, sufficiently homogeneous, stable. And then you have to somehow determine the reference values, you know, and assign uncertainties. As I already implied, it's not easy thing to do, needs competence, time, and there are not so many places on this planet where the certified matrix reference materials are produced at high level. And it's governed by a number of different standards, you know, which typically the producers have to obey. Now, for making the material, or simply creating the body of a material that you will be using, can be done in two main ways, two different ways. One is formulation. Formulation means that you take pure components, you mix. So for example, I mentioned here these solvent mixtures, for example. Then you find very pure acetone, very pure acetyl acetate, etc. You weigh carefully those amounts and you mix, you know, mix well, and now you have your reference material. You know. But it, of course, only can be used for simple matrices. There's no way to do formulation with meat. You cannot take proteins and fats and mix them and then get something that is like meat. You cannot make soil like this. You cannot make wood chips, and you cannot make rice, flour, blood plasma, etc. So most of the materials you cannot make. But as I said, solvent mixtures, no problem. Yeah, alloys. Yeah. Drinking water also can be made by formulation. So you can take ultra pure water and add different salts in it, which mimic the salt composition of drinking water. Voila, there you have drinking water. So formulation is limited, but it is easier to determine reference values. So for example, if you do this solvent mixture thing, then you can very carefully weigh those amounts, and you don't need to run any analysis afterwards. You can prepare by weighing, which will be very accurate if you use pure materials. Yeah. So that you can quite easily get reference values, and they will be quite accurate. That whenever this is possible, formulation is actually a good approach. But sadly, most of the time it's not possible. Then the second approach, of course, is using the natural material. It can be now natural, or it can also be incurred, etc., fortified, etc. So you bring some soil to the facility, and then the soil is managed, homogeneous, etc., etc., etc. And finally, this soil is the certified reference material. Of course, here this can be done with any matrix. Yeah, you can also make drinking water reference material like this. But of course, any reference values now need to be determined by measurements. You cannot calculate them from the amounts that you add. And now I will give some principles and some steps how matrix CRMs are produced. And I will only explain at this point the, let's say, the most difficult type of CRMs, the matrix certified reference materials from a natural materials, meaning not formulation, but from like soils, soil, plant leaves, etc. So this is the most complicated type to produce. And we will later on see that interlab comparison samples are prepared also in somewhat similar. So first of all, here are some things that are not, sometimes not so well known. So usually nobody produces certified reference materials in such a way that, okay, I make 10 bottles, what I can send to 10 customers, because it would be prohibitively expensive. It is a very expensive thing to do. All the facilities, etc., is expensive. And determining the reference values is also an expensive thing to do, because you have to hire expert labs, or you have to be expert lab yourself with highly competent and skillful people, very good instrumentation, etc. So that it only makes sense to produce CRMs in large batches, hundreds or thousands of bottles, which you can then send during several years to many customers, and earn back the money that you put into development. Yeah. The next thing, you have to prepare the whole batch at the same time. So you cannot do so that, okay, I bring here 50 kilos of soil, and now I will today do with 5 kilos, tomorrow with the next 5 kilos, and so on. No, because then those different sub-batches will eventually most likely have different reference values. And you again end up with different CRMs. So that this homogenization, mixing, etc., has to be done at the same time with the whole bulk material. And that material is not typically in grams, it's in kilos, in tens of kilos usually. Meaning, you cannot do this with like a kitchen blender. Yeah? You need facilities, you need like pilot plant scale of facilities which are able to process large amount of material. The last thing, every CRM, every matrix CRM is unique. You cannot remake it. So suppose you, hey, I want to do soil CRM. Yeah? I bring some soil, yeah, and now I make my 2,000 bottles. Now I'm selling them during some years, and now I've sold all. I don't have any left. Okay, I will now make a new one. And you can try to do exactly the same way. You take the soil from the same place and bring a lab and do the same, but you do not get the same values. Because all those labs who make the measurements for you, they also have measurement uncertainties. They certainly will not get exactly the same value. And of course, if you take even soil from very similar places, then overall it still will be slightly different soil. So that all these certified reference materials, they are unique. The next one can be very similar. Yeah, it can be very similar and suitable for the same applications, but its reference values will be different. And uncertainties might also be different. I'll come to that later on. The uncertainty is also a tricky thing. You cannot really, how would I put it? You cannot know beforehand how good uncertainty you will get. So that every batch is unique. And because of all of this that I mentioned, it's not a good business. So making certified reference materials business-wise is not a good business. And most producers actually are not purely private enterprises, but they're supported by some governments or some organizations. For example, NIST, N-I-S-T, National Institute of Standards and Technology. I think you all know what NIST is. It's in the USA. NIST is a governmental body. Yeah? NIST is one producer of the reference. Then there's the JRC, or Joint Research Center, which formerly was had the branch IRMM, Institute for Reference Materials and Measurements. That is a body that belongs to the European Union. So Europe, it's funded by the European Union. It's not a company as such. Then there's LGC in the UK, Laboratory of the Government Chemist. That one operates as private company, but it still has huge contracts with government, so that it does not produce CRMs on purely commercial basis. It's still like subsidized to some extent. And that is quite true for most producers. Not all. Some are purely commercial also, but most are not. Yeah, please, but take some kind of thing.
Just out of curiosity, the two ways of production, we have formulation and the natural method. From the way you explained the natural method, it seems it's more complicated than the formulation.
True.
So does it mean that for the uncertainties, there's a tendency that formulation gives a, I don't want to say a lower uncertainty, but a more accurate uncertainty compared to natural materials?
It can give, yes. So if you, okay, let's take that same drinking water. Yeah? If you take highly pure water and highly pure salts and weigh very carefully and mix together, you get lower uncertainties of concentrations of elements in drinking water than if you simply take this water from this tap, 100 liters, and now you bottle it into bottles, send to the expert labs, and expert labs will do determination for you, and then you calculate the uncertainty, then that uncertainty will be high. Okay, I'm not saying always, but most probably will be high. So that formulation is a very good way, yeah, but sadly it's quite limited. Yeah, you cannot. Most matrix CRMs you cannot do via formulation. So here is now the like scheme how to produce CRMs, not via formulation, but from, let's say, natural material. Let's look at it. Yeah. First of all, you have to collect the material. And it's, as I said already, kilos and usually tens of kilos of material that you need. You need to sort of initial homogenization, particle size reduction. For example, if it's soil, you throw out big stones and maybe sticks of wood and so on. Yeah, make it like more or less okay, and then do some initial homogenization. Then the next thing is usually drying. Not all CRMs are dry, but most of them are. And drying is very important to avoid microbial growth. And I'll come back to that later on, but already now I mentioned that usually you make thousands of bottles. You cannot sell all of them in a week or in a month or even in half a year. Usually CRMs are made in such a way that they can be stored for many years, sometimes for tens of years, meaning stability, long-term stability is extremely important. Even now, you can still buy CRMs that were produced in 80s and 90s of the last century, meaning they are something like 20 to 30 years old and still okay. But they are still okay because they were very carefully made. Yeah? Yeah. But not everything can be stored so long, but some things can. Yeah? So the drying. Now, which way you dry depends on the matrix. And as you see, I have here now two sets. These are robust things. Minerals, soil, etc., and suppose mostly like determining elements. So you can take soil, and if you don't want any organics in determine organic but elements, then you can oven dry soil, and all is well. But here, if it's some kind of a bio CRM, for example, some delicate analytes or very delicate matrix such as meat, etc., you cannot really dry well in oven. And then this should be done using freeze drying or lyophilization, as it is also sometimes called. So the two different drying possibilities. I make a note for myself to do some changes here. Then the next important thing is that certified, such matrix certified reference materials should be homogeneous, and particle size should be small and as homogeneous as possible, so that you have similar size of particles throughout the bottom. This is quite interesting and important thing. Let me show you why it is important. Suppose you have some kind of bottle here, and suppose now you have different particles of different sizes. And suppose you now shake it. What happens? Suppose this is some kind of cup, you have like sand and stones and things, and now you shake it like this. What happens? Has anybody tried that on a beach, for example, when you were a child? When I was a child, I did that experiment. It's an interesting one. If the density of this material is roughly the same, what happens with the particles? Interesting, you don't know. So, if the density of the material is roughly the same, then what happens after you just shake like up and down? You will have small particles down here, somewhat bigger particles here, and the biggest ones will be on the top. So they will be clearly segregated by the size. And this is not good. Because suppose now you do all this processing, and now you finally have a big bulk of the material, and now you start filling the individual bottles. If you have bigger particles on top and smaller particles on bottom, this may mean also that those particles that are bigger may have systematically slightly different chemical composition than those on the bottom, and you have a trouble. Yeah? So such segregation is not a good thing, and for that reason it is very useful if the particle size is more or less the same throughout the bulk. And typically it is considered a good particle size is average diameter something like 0.3, 0.4 millimeters. Because if it's too big, then it's difficult to achieve homogeneity. So there will be let's say when you withdraw some amount, there will be too few particles on your spoon or on your spatula. But if it's too small, then the particles will behave like a dust. And this will mean that the ratio of area to mass will be very high. And such dust-like material will absorb on its surface all kinds of things from the air, etc. So too small also is not good. Yeah? So let's say it's somewhat less than 1 millimeter on an average should be the diameter. This is typically the best. And then this is done with different kinds of mills. Now, if it's a meat which is freeze-dried, the meat which is freeze-dried is still such strange matter, you cannot mill it well. So for that one, people use something called cryo-milling. where the mill is cooled with liquid nitrogen, so that everything becomes very brittle, and then you can mill meat. You can also mill rubber at that temperature, etc. So at that very low temperature, all kinds of things can be milled. But these minerals and things can be milled using a normal, usual mill. Okay, once that is done, now sieving is specifically for getting fraction with similar particle size. So sieving finally does such a thing that you will get one fraction which you like, average particle diameter of this kind. Then that is the fraction you finally are going to put into bottles and sell to people. And now after sieving that large bulk material, and again, please note, all those things are done with the whole bulk at the same time. So those kilos of material, they go to drying, and then they go to sieving, and so on. Then it's still homogenized in some kind of, again, mixer or blender or whatever it is. And finally, the material is bottled. So put into individual bottles or packages. It can be bottles, ampules, or plastic bags in some cases. These bottles eventually are those that will be sold to people who buy this year. So this was it in a nutshell. I will show you some photos in a moment, but Faber.
You just stated oven drying and freeze drying. So I was curious, can't we use a drying for any of the drying processes? Because for certified reference material.
Yeah, can be. Also can be. And actually oven drying also can be done in vacuum oven, for example, which enables using lower temperatures. Yeah, there are more possibilities. Indeed, these, as I maybe did not stress this, these are examples. There can be different things. As I said, for example, not all CRMs are dried. There are also meat CRMs which have been pasteurized, so heat treated at high temperature and sealed accurately into plastic bag meat. And it's not dried, it's slimy water containing meat, the meat that you find in shop. That also can be a CRM. And if it's made well, it can still be preserved for several years. Yeah. So as I said, these are some examples how, in principle, this kind of thing is done. Any other questions? Okay, now I did not mention, but this scheme comes from this same Institute for Reference Materials and Measurements, which now is called JRC GALE. JRC is Joint Research Center. It's the research arm of the European Commission, and GALE is the name of the place. Yeah, it's a very small town in Belgium where this is located. But now, let me ask you this question. If you do meat analysis, the meat that is brought to your lab is not freeze-dried, yeah? It's the usual meat, yeah, which you see in shops. And now if your CRM is freeze-dried, can that be a problem? Can that be a problem? They're not the same matrix, yeah?
I think it depends on the elements, the techniques, because if it's influenced by the solvent, then it is a problem. But if it's not, then that is okay. It is not.
In principle, correct, yes. In different situations can be different. But overall, yes, it can be a problem sometimes. So certified reference materials oftentimes tend to behave better than your real samples, even if the matrix is formally the same, because they are better homogenized, very uniform particle size, and so on, which are good things. Of course, freeze-dried meat can be made into water-containing meat quite easily. If you add water, it is terribly hygroscopic. It will suck water in and become again more or less the same meat. So that if you take it out of the bottle, you weigh quickly so that you know how much you have. And now you add water, then in some time it turns into something which is more or less like meat again. So you can work this way. And this is how usually it's done. But yes, sometimes, as I said, CRMs sort of behave better than real samples. And this, of course, sadly cannot be fully avoided. Yeah, this is how it is. Now, some photos. Yeah. Here you see some kind of a blender, and now you see this is certainly able to accommodate maybe 100 or 2 or maybe even 300 kilos of some material. Quite big. This is a cryo mill, and why it is covered with frost is that it's at very, very low temperature. And this is here some kind of sieving operation. And you see that this person is working in a glove box. And glove box in this case may be, I don't know exactly why here, but I guess that it may be because freeze-dried materials are terribly hygroscopic. So that they probably want to work in water-free conditions in such a way that water vapor cannot exist. So, because otherwise, if water vapor from air is absorbed into this material, 2 nasty things happen. First of all, the mass will be higher because of water, and the reference values will not be correct anymore. But the second thing is that we cannot sieve it if it becomes slimy. If it becomes sticky and slimy, you cannot sieve. You can only sieve if it's really dry powder. And if it's hygroscopic dry powder, you cannot do much manipulation with air because water will be coming in immediately. Here you see a vacuum oven. Here you see some kind of mixing thing. Here I always have this question, why are there different bottles? It should actually be one bulk, but maybe this is some pre-mixing so that the different bottles are okay. This mechanical is an interesting thing. You see, these bottles are fixed here, and this mechanical setup enables rotating this way, and this way. So rotating randomly in all possible different directions, which is very good for mixing. This is ampuling setup. So this is a machine that seals ampules. This is a bottling line, and these are here CRM bottles. And here you can see some examples what the CRMs can look like. Yeah. Very often they are bottled like this or like this. This is a wine CRM, by the way. Then they can be ampules. Also, this is an interesting one. I don't know why it is so segregated, but maybe this is some kind of material which before use you have to shake well to make it homogeneous again. Yeah. And this is also an interesting place. This is a storeroom, and you see it's a big one. Yeah. So you see it's very long, and these are these movable shelves, yeah, so that there would be more of them in the room. It's huge. And this is one more thing which makes CRM production quite expensive. You need to have big storerooms, because if, as I said, you are going to sell every batch for maybe 10 years, you have to have a place where you store all this during 10 years. And this here seems to be at room temperature, but some of them need to be stored at reduced temperature, maybe at +4 or maybe even at -, temperatures. Meaning you need to have a huge cool or huge cold room, which are expensive to have and expensive to maintain. Yeah, this is it. Any questions here? Yes, please.
In the case of the storage, do they have to perform some revalidation of the concentration, like often?
This is sometimes done, yes. Now, I did not plan to speak at this point. I planned to speak about that later on. But since you ask now, let me already immediately then answer. So we will now, next thing, we will come to the reference values. And then I will explain what are the things that are taken into account, assigning the reference value and uncertainty. And the point is that during the shelf life of the CRM, the reference value has to be within the uncertainty range with high probability, as we always have it. Yeah, these reference uncertainty ranges are always probabilistic. What typically they do is that they establish, and I explain how, they establish, okay, during 10 years of storage, the value will be within this uncertainty range with 95% probability. And this is what they say. And then throughout that 10 years, they will not revalidate. So what happens then is that if 10 years pass and they have still a big stock, a lot of bottles left, then they may want to revalidate them so that they could continue selling. But if not much is left, then they probably will not do, because it's, again, costs money. Yeah? But then there's a second possible approach that is used by some producers. Those producers record all buyers. So whoever buys this CRM gives the contact data. Yeah? And that CRM does not have any shelf life limitation, but the seller, the producer, monitors and informs everybody, alert, alert, yeah, now the value is, we made measurements, now please use this new value. It can also be this way. Of course, it's, again, quite expensive, yeah, to maintain all that and revalidate, etc. But yes, to your question, revalidating or recertifying, as they call it actually, recertifying sometimes is done and makes a lot of sense if the material is sort of stable, but by the end of the originally declared shelf life, you still have maybe 1,500 bottles left, then yes, recertifying might make sense. Did I answer? Okay. So now, here in the previous slide, we only explained how the material is made, yeah? And as at the end, let me go back for one moment. At the end of this, you then have those thousands of bottles, yeah, in the laboratory, okay? But those bottles don't yet have any values. They don't yet have any certified values. So the next thing to do now is establishing the reference values. And most of those people who are working in this area call it certification. So certification of CRMs. And again, we have these two situations. Formulation, I actually already explained. Yeah, here you use weighing, etc. data. I will say a few more things on the next slide. And then the second possibility is measurement by different laboratories. If possible, usually producers try to organize an interlaboratory comparison measurement. ILC stands for interlaboratory comparison measurement, which means that they send the bottles to different expert labs and ask each of them, for example, determine lead content in this water. And then those labs send back the results, and then they averaged, and from those lab results also the uncertainties are calculated. I would say that prominent and well-respected producers mostly use this way because it gives eventually much better reliability than just making the measurement at one single lab. Because any lab can occasionally make mistakes. But if it's 8 laboratories that are involved, for example, then it's unlikely that all 8 will do it wrong. So, formulation. As I already mentioned, it's usually based on weighing data. Weighing can be done very accurately. So usually you can get highly reliable reference values quite cheaply. You don't need to do that interlab comparison. You can do it in your own lab. But of course, homogenization is critical. Luckily, again, formulation often is used with materials which so problematic to homogenize. So for example, again, if you want to make a drinking water, you put soluble salts into water, then homogenizing aqueous solution, not really a big issue. Yeah, it still needs to be done very carefully. It's not just that you shake 2 times and now you go. Yeah, it's more than that, but it's still easy. And of course, what I already mentioned, yeah, you only can use it for limited number of quite simple matrices. Most matrices you cannot. So that more common way is measurement, interlaboratory comparison measurement. So what is typical of this? First of all, we will have a whole separate part of this course on interlaboratory comparison measurement. I have, during the years, sometimes done ILCs before CRMs, sometimes CRMs before ILCs, and for many years I didn't know which way to do. But now I sort of have converged to the situation that probably I should do CRMs first, and then ILCs later on. You know? But in any case, we will still come back to interlaboratory comparisons. But let me say that this is a special kind of interlaboratory comparison. Most laboratories never participate here because only expert laboratories are invited, and it's only on invitation. When you do this certification campaign, then it does not work like this, that any lab can sort of sign up, oh, I also want to participate in the certification campaign. No, they only invite, it's only on invitation and only really experts. Then the organizer usually wants to attract people who use different techniques. For example, if it's trace elements, there's certainly somebody with ICP-MS. If concentration allows, there's certainly somebody with ICP-OES. Maybe with XRF, if it's not ultra-trace analysis. Then maybe neutron activation analysis, and maybe some electrochemistry on top of that. So it's very good if different labs who participate use different techniques. Of course, again, we must remember that if it's method-dependent reference value, then there's not much freedom. Everybody has to use the same method. But if it's method-independent, then this is very good. For example, polynuclear aromatic hydrocarbons, known carcinogenic compounds, they can be determined by GCMS, they can be determined by LCMS, and also by LC fluorescence. All these 3 techniques are used. And now, if somebody will produce a CRM of a PAHs, then usually they try to find somebody with GCMS, somebody with LCMS, and somebody with fluorescence also, so that they could compare. Very important, because different techniques can have different biases. And if you have only one technique and everybody's biased into one direction, your reference value eventually will be biased. Now, let me come back for a moment to these trace elements. Those of you who took atomic spectrometry, you remember in ICP-MS for many elements, there were certain specific interfering elements. And those interfering elements always can introduce bias. But if there's another person with ICP-OES, where the interferences are completely different, and the third person with XRF, where in turn, again, completely different pattern on interferences, then it's very useful. Because somebody's up here, down, so there's some kind of scatter, but not everybody biased into one direction. Bias, very bad thing. Yeah. Okay, then on the basis of those labs, consensus value is calculated, but it's not necessarily simple arithmetic mean. It can be something more sophisticated, such as median, mean after rejection of outliers. It can be some weighted mean, etc. So this consensus value then is the reference value. And of course, the same CRM can have different reference values, for example, for different elements. Yeah? If you make trace element CRM, it can maybe have 20 or 30 certified values if a number of elements are determined. And uncertainty is then evaluated. And this uncertainty, of course, has to take into account disagreements between participants, meaning discrepancies between their values. This is well, quite obvious. And there is usually a technical discussion where people really discuss in depth how you did, how he did, how she did. Okay, did you dissolve complete? Maybe your digestion was not good enough, so you lost some analyte which was not really dissolved, and your value is now lower. Yeah, maybe we should exclude you from this, etc. And now about the uncertainties of these reference values. As I already said, certified reference materials only can be considered correct if their values have uncertainties. So uncertainty estimates always are mandatory. And now the uncertainty is here interesting. So it's very important sentences here. The uncertainty range has to cover any sample. First of all, you have one bottle. You can take several samples from it. The content in any of these samples has to be covered by the uncertainty range. Why I'm saying that? There's always some small, tiny inhomogeneity, so that you take one sample, it's slightly different than the next sample. Then the bottles themselves are different. Yeah? Every bottle is slightly different than the next bottle. And finally, during the whole shelf life, meaning the person starting to use the CRM tomorrow, and somebody starts in 7 years, where slight changes may have happened, all these changes also have to be covered by the uncertainty estimate. Please raise your hand who thinks that understood what I wanted to say. Okay, thank you. People on the internet. Conrado. Yeah, okay. Yeah. So that this uncertainty range is quite an umbrella, actually, yeah, which has to cover the different bottles, etc. So this cannot be done in such a way that, okay, I take one bottle out of those thousands. Yeah, now I analyze that one, make careful uncertainty. Oh, here you are. Yeah. You have to analyze bottle-to-bottle variability. You have to make long-term stability tests, etc. Also, what I did not mention, I will write this here. I should have it in the previous slide. One moment. So during this certification campaign or this certification, every lab which participates here gets usually several bottles randomly selected from the big amount of bottles. So usually those bottles are bottled like in sequence. They are usually getting some numbers, yeah? And now from this bottling sequence, from random places, people send the bottles to the certification campaign. No? And so, since the uncertainty needs to cover all these things, then the uncertainty components, if you wish, or uncertainty sources are here. First of all, uncertainty of the analysis itself. Then uncertainty due to between bottle variability. Uncertainty due to some inhomogeneity within the same bottle. Of course, between bottle variability largely covers this also, so that these two are usually treated as one component. And finally, uncertainty due to possible instability. Any questions? If not, I have a question. Why do I use here the word possible? Hint. It's similar reason that we had with Nordtest. Remember, in Nordtest there was the word possible in many places, and some of you were uncomfortable with that possible. Yeah? Here again we have possible. Why?
Because we cannot study for like 10 years, so we just study like long-term stability or force degradation or something to obtain like possible instability value.
You are quite correct, yes. So often these stability studies, and I will show you one, will lead to situations that we maybe don't even know if there is any decomposition. But during that study, we also need to measure how much it changes. All those measurements have uncertainties. So that very often we end up with something, okay, yeah, it sort of seems to be stable, but maybe it's not. So we assign some uncertainty level just to take into account that maybe it will decompose to some extent. So that, yes, as it was with bias, remember we spoke with possible bias, and I explained that really rigorously determining that, yes, I have a bias and this is my bias can be very difficult. In many cases, you don't really know eventually whether you have a bias or not. Put uncertainty due to possible bias, as it was in Nordtest. And here, uncertainty due to possible instability, because we don't know exactly whether there is the instability issue or not.
So I have a question.
Yes.
Regarding instability, like since you said CRMs last for a long period of time, has there ever been a situation whereby, like maybe after 10 years, the CRM like we analyze to get the reference value, and there is a discrepancy between the initial value and the present value? I don't know if you understand my question.
You mean, is this possible?
Yes,
It is.
possible?
Yeah.
And if the discrepancy is large, what happens to the CRMs then? Are they recalled from the market or?
So yes, yes, this is possible. It's not very common. And of course, the producers try to minimize this probability. Typically, so first of all, the producers usually have a lot of experience. So for example, if they make a milk powder reference material today, they probably have done it 10 years ago and 20 years ago. So they have something to stand on. They know how they behave. If it's the same analytes and they simply are making a new batch, then they have very good understanding how the CRM behave because they already have the previous batch. Yeah? So that it's not very common. But yes, it is sometimes discovered, and then usually it's announced. I already mentioned this one possibility that the producer monitors the values and then informs all the participants. This is one possibility. The other possibility is that participants are not informed, like personally. But if this recertification takes place, then there's again some kind of information source, website usually these days, yeah, which says, aha, this CRM, I don't know, X6027, yeah, this now has been recertified, yeah, and you should, yeah, now, from now on, use this value, yeah. So yes, this can be done like
that. Is the uncertainty range just broader, or is it bigger to one side? Because if it's instability, it should go lower.
This is the, you are touching upon an extremely important question, which up to now I have left out of this course completely, but I have actually considered to bring it in. And this is the whole range of topics related to asymmetric distributions, meaning asymmetric uncertainty ranges. So that the uncertainty range would not be plus minus 10 milligrams per kilogram, but would be, for example, plus 5 minus 15 milligrams per kilogram. This is quite rare to present results that way, but sometimes it's done. But this, of course, needs that the uncertainty range is, the distribution function is really investigated. I'm saying very important. You say, hey, wait a minute, but why are you not teaching this to us? It's very important or extremely important. You see, it's very or extremely important fundamentally, but in practical lab, what people usually do, if the uncertainty range would be plus 5 minus 15, it would be plus minus 15. So that usually they simply like cover it, simply expanding on one side. And since at routine laboratory level, this is okay, you see, we are already now lagging behind. Yeah, it's difficult to fit all the material into the course, so I haven't touched upon. But now let me come to your point. You are right. This might make sense sometimes, yes. But if there is some kind of decomposition, then usually what they do, they still give symmetric uncertainty range, but they already put the value itself into like sort of lower to account for the fact that it will soon start getting lower. And then there's another interesting thing, that decomposition does not always lead to decrease of the value. For example, if the matrix decomposes, it can produce some kind of interferent, which leads to increased value. Moreover, decomposition can lead to increase of the analyte content. And the very good and very real example is that in plant oils, vegetable oils, free fatty acid content is an important parameter which is monitored. And many plant oil CRMs, they have free fatty acid content determined. But now, typical decomposition of plant oil is hydrolysis. What happens during hydrolysis? More fatty acid is produced. So that in this specific case, decomposition leads to increase of analyte content. Of course, this is not very common. This is like quite specific example. But yes, it can happen also this way. So that usually they don't make asymmetric distribution functions. Okay. If no more questions, okay, we are almost done, but let's see. Yeah, I will still explain this formula. I'll go a little bit over them. Yeah. So here is how you or how labs typically calculate the uncertainty. This is the standard uncertainty due to the analysis. It includes the analytical method uncertainty and also discrepancies between participants. And I'll come to that either today or next time. This var is all kinds of variability. So in homogeneity within the bottle and variability between bottles. And stab is stability or instability uncertainty. And K is coverage. Yeah. So this is quite logical way of calculating. And now, uncertainty due to the analysis, it's not straightforward because usually several labs participate. The results always differ to some extent, although all of them have their own uncertainties. But it's also important to consider they all analyze different bottle sizes. And secondly, they all make some mistakes so that you have to like summarize all these things. And of course, different techniques in turn have different uncertainties. So it's not possible to do it in such a way that you calculate some kind of average, arithmetic average of the uncertainties. It has to be done in a more sophisticated way. And also, sometimes, even in expert laboratories, sometimes problems can happen. And it sometimes may be necessary to exclude some expert lab results if they find problems. And here, let me give you some examples. So, suppose these are now the 8 expert labs that did the analysis. Each of them got the result, yeah, and you see very different uncertainties. But now, if these 2, they seem to be most distant from all the others, if these 2, in the results of these 2 labs, deficiencies were found, specifically some interference from something made the results look higher. Yeah? And if that can be found during the technical discussion, then that's a good ground for excluding these 2. And okay, here the uncertainty is very big, so we probably don't need to worry too much that this goes over. But then the uncertainty range can be made, let's say, more or less from the uncertainties of these 5 laboratories here. Yeah? Oh, sorry, I said it's 8. No, it's 9 laboratories. Yeah? Okay. So this is actually a good case because the agreement of this lab, this lab, this lab, this lab, and this lab, considering also their uncertainties, actually is quite good. No? And quite reasonable uncertainty. But it can also go less favorably. If there's no way of knowing, finding any problems, then we cannot exclude that maybe these labs did something wrong and they have losses. Lost analytes, maybe not incomplete extraction. Yeah? Maybe these were the only gurus actually in the group. We don't know. And now, usually what they do, they simply expand the uncertainty, which is unfortunate because here you see the expanded uncertainty is more than already significantly higher than 10%. And this already will have influence what the CRM can be used for. Because CRM with too high uncertainty is not so useful anymore. You cannot find that there's discrepancy because if the uncertainty is so high, then very wide range of values will be compliant with the uncertainty. So not so good. But yeah, there's not much to do. Of course, they can repeat the whole certification campaign. The main reason why it's not so often repeated, of course, is that it's costly. Yeah? Then you need to pay everybody again. Yeah, and it takes a lot of money. Because in this kind of work, usually laboratories get paid, or it is done in. Oftentimes, this is also done in some kind of. Let's say they don't get paid specifically for this work, but they participate in the framework of some bigger project or contract where everybody has some preset tasks and preset money that they get. And if suddenly they need to perform some task 2 times, they might not be happy. So we stop here today, and next time we look at the variability and also this instability thing. And next time will be tomorrow. Yeah. So thank you. And unless there's any quick last minute. Yes.
One question. Like, is there a way of getting, like, can people apply for a grant to get money to produce CRM?
It is possible, yes. Yeah. Production of CRM can also be part of scientific research projects. Absolutely. Yeah. So, if no more questions, then thank you, and we meet again tomorrow. And then try this uncertainty of linear regression, I hope.